So I'm going to share screen with you. And we're going to try. I'm just going to press various buttons. So I want to just begin by telling you what I'm going to do in this talk and what I'm not going to do in this talk. I'm simply going to go through the scientific basis for carbon offsetting, or to use the Swedish expression, klimatkompensation. I'm not going to talk about whether it's a good idea or a bad idea. We're going to draw those conclusions ourselves. And there's going to be an interesting discussion, which Maria and Iris will lead, where we'll delve into those questions. But I just want to start by giving the science behind the idea of carbon offsetting. And I want to talk quite a lot about timescales, because they're going to turn out to be really important. I'm just going to see if I can actually change slide. Yes, I can. Okay. Now, the scientific basis for carbon offsetting comes from this rather hideous diagram. And I'm not going to dwell on this diagram because it's really hard to follow and understand. But by the time we're done, we're going to understand the key parts of this diagram that we need to work with. This is the carbon cycle as published by the IPCC. It shows how carbon moves around the Earth system. It's got black arrows, which are indicating natural movement of carbon, and it's got red arrows, which are indicating what we've changed to the climate system. Now, it's really, really hard to work with this diagram and to understand it. So I'm going to break it down into the part we need to think about when we're talking about carbon offsetting, and that's the atmosphere. But before I can even do that, I need to explain the units we're going to work in. Because if you look at this diagram, you'll see this unit PGC per year, petagrams of carbon per year. Now that's a petagram. What is a petagram? These are unfathomable numbers. And I'm going to try and get us to get a visualization of what we mean when we talk about moving a petagram of carbon from one part of the Earth to another. So let's try and compare it. Let's try and think of a petagram as something that's a little easier for us to visualize. Well, we can look at the number. A petagram is 1,000 grams. That's kind of a lot. Or 1,000 million kilograms. That's also kind of a little difficult to visualize. It's a billion tons. What does a billion tons look like? Well, there's something that we haven't had to use for the last little while. It's a jumbo jet. They're all grounded. But anyway, if you weigh one, it weighs about 200 tons. I don't know whether that includes the passengers or not. I haven't checked that. So that one jumbo jet is 200 tons. One petagram is 5 million of those. So that's equivalent in mass to 5 million jumbo jets. So now when we talk about moving a petagram of carbon, try and get your head around the fact that that's a lot of carbon. And then look at the size of a tree that you're going to plant to solve petagram problems. So let's just get that 5 million jumbo jets weight in our head before we move on. Okay. Right. Let's now look at the carbon cycle. And the only part we really need to worry about is the atmosphere, because that's the part we're messing up. And I'm just going to move I've got all your pictures here and they're in the way. Look, I can move you down there. Much better. Good. So the atmosphere, now I'm going to show this figure twice. The first time I'm going to show this figure, I've used the word pre-industrial. What do I mean by that? That's before 1750. That's before we started having a major effect on Earth's atmosphere. At that point in time, Earth had 589 petagrams of carbon in the atmosphere. Note that's carbon, not carbon dioxide. If you want to turn that to carbon dioxide, you multiply by 44 and divide by 12. And anyone who can tell me at the end of the lecture why you do that gets a Researcher's Desk Award. So, where's that? Let's have a look at the carbon coming in and out. Well, there is only one natural source of carbon to the atmosphere, and that's volcanoes. All other sources are just moving carbon around. Carbon comes to the atmosphere from volcanoes, and 1/10 of a petagram of carbon per year, on average over long time scales, comes from volcanic eruptions. And exactly the same amount is removed from the atmosphere by the weathering of rocks, averaged over hundreds of thousands, millions of years. So that's in perfect balance. 1/10 of a petagram in and 1/10 of a petagram out. That's what we like. We like balance. That's good. So nothing changes in the atmosphere. We also have a much, much faster exchange of carbon. There's a carbon flux from the oceans. Carbon going degassing from the oceans and from lakes. And that's putting in together 1.7 petagrams of carbon per year. And there's a balancing flux to the land, processes such as photosynthesis, 1.7 petagrams of carbon per year. So if we look at that, that's exactly the same going in and going out. It's much bigger than the volcanic carbon flux, weathering carbon flux. It's much faster. And if we add all that up, add all the arrows going up as pluses and the arrows going down as minuses, you get to 0, which is exactly what we want to get to. No change. The atmospheric CO2 concentration remains constant. So now let's look at that diagram one more time. But we're now going to look at the average for the time period 2000 to 2009. At some point in the not too distant future, we should be able to replace that with 2010 to 2019. But we don't have the numbers for that yet. So let's use 2000 to 2009. So what's the difference? Well, there is 7.8 petagrams of carbon per year added from burning fossil fuels and making cement. There's another additional 1.1 petagrams of carbon per year because we change how we use the land. We changed land that was a carbon sink, that's something that takes carbon out of the atmosphere, and make it into a carbon source. That's something that puts carbon back in the atmosphere. So that's 8.9 petagrams of carbon per year being added to the atmosphere. Remember the jumbo jets? Okay, so that's 8.9 times 5 million jumbo jets worth of carbon being added to the atmosphere by us every year. Where does it go? Well, actually, not all of it ends up in the atmosphere. It's one of the things we have to keep in mind. 45%, that's 4 petagrams of carbon per year, are added to the atmosphere. It's 2 million jumbo jets in mass added to the atmosphere. The rest causes the carbon flux now to flip from the, so carbon from the, now carbon goes from the atmosphere to the oceans. But before, it was going the other way around. That's what causes ocean acidification. That's why small shells in the oceans are dissolving, because that carbon comes in and makes the ocean acidic. And we have an additional carbon flux to the land. So that's how that carbon gets distributed in the Earth system. Okay. Before we move on and look at carbon offsetting, we need to have a couple of problems in our mind. And I'm using problem in the English sense of the word. I'm not implying it's negative or positive. I'm just stating it's a challenge. And it's something we need to be aware of, like problem solving. As I say, I'm not putting any value judgments in this talk. We're going to do all that afterwards. Here's the problem of time. It takes millions of years for the coal to be formed. Coal is a rock. It's formed from squashed up plants. You can think if you want more fun, it's formed of squashed up dinosaurs. Doesn't really matter. It takes millions of years to make. And we burn it and turn it into CO2 and take it out of the rocks and put it in the atmosphere. We do that on a timescale of tens of years. I think you can easily see there's an imbalance there. It takes millions of years to form, and we convert it to something else in tens of years. We've got a geological process on the left and an anthropogenic process on the right. Geological is natural. Anthropogenic is what we do, what we cause. And it's exactly the same with cement. It's just different starting materials. Small fossils, small shells in the sea, in millions of years, they turn into the rock called limestone, like this beautiful piece from Gotland. Calcium carbonate. Look, you can see there's carbon in there in the chemical formula. And when we make cement, all we do is we take that calcium carbonate and heat it up so the CO2 gets released and we're left with calcium oxide, lime, cement. We do that in tens of years. We create the same imbalance between geology and the anthropogenic timescales. So that's the problem of time. So when we're thinking about moving carbon around, remember we're moving stuff that usually moves around over millions of years, and we're moving it around over tens of years. So we need to have that problem of time in our mind when we start thinking about offsetting. And that might not seem clear yet, but it will do as we move on. Then I want you to be aware of the problem of mass. I think I probably emphasized this a lot already, but it's super important, so I want to emphasize it one more time. Fossil fuels and cement production. You'll sometimes hear people saying volcanoes are like a major source of CO2. They are. They release 1/10 of a petagram of carbon per year to the atmosphere. That's like 500,000 jumbo jets worth. But we do 7.8. That's 78 times as much. So we have a problem of time. It's all happening too fast. And we've got a problem of mass. It's too much. And we have to have both of those in mind before we talk about offsetting. So now let's look at the effects of moving all that carbon around. So here's our pre-anthropogenic, pre-industrial atmosphere with its imbalance with 589 petagrams of carbon, which by the way would give us 280 parts per million carbon dioxide in the atmosphere, which is where we should be between two glaciations. So it's just spot on where it should be. But if we want to think about the effects, we want to also think about the other reservoirs. Where else can carbon be? Well, the oceans is a great place, has a lot of carbon. It's got 38,700 petagrams of carbon. Marine sediments, your picture's in the way of my number, I need to move you, has 1,750 petagrams of carbon. Vegetation has, we're not quite sure, somewhere between 450 and 650 petagrams of carbon. Soils, somewhere between 3,200 and 4,100 petagrams of carbon. Rocks have lots more carbon than anything else, 65,500 petagrams of carbon. Now, one part of rocks, and the part we need to think about when we're talking about rocks, is fossil fuels. Read the name, fossil. What does that mean? It comes from rocks. Fossil fuels, between 1,002 and 1,940 petagrams of carbon. Those are the estimates. You can see there's a huge range. We don't know how much carbon, how much fossil fuels there actually are. But it's somewhere in that range. So that's the natural balance. That's what the Earth should look like. Now let's look at add all the change from 1750 to 2019. Now the numbers here differ slightly from the IPCC because I've added the last 10 years. So if you do compare with the IPCC, you'll get different numbers. But that's because I've added the last 10 years to get it up to date. So 427 petagrams of carbon have been burnt. That's about somewhere between 1/2 and 1/4 of the fossil fuels that exist on Earth have been burnt. And land use changes contribute an additional 18 petagrams of carbon. So that's that mass of carbon. And as I said before, it doesn't all end up in the atmosphere. A large chunk does, 272 petagrams, and the rest ends up in the ocean. So that's the effect. We've just moved a vast amount of carbon around. And if we're now going to think about carbon offsetting, we want to look at it and see, well, we look at the atmosphere and say, okay, we've added 272 petagrams of carbon. When we're talking about carbon offsetting, what we're really talking about is saying, let's get that carbon from the atmosphere back into one of the other reservoirs. So we need to move it into oceans, marine sediments, vegetation, soil, or rock. That's what we're actually talking about when we're saying carbon offsetting. Now I'm going to look at a few options for that. before I do that, I'm not going to look at oceans. And I've got a good reason for not looking at oceans. And that's because it's been tried and tested in experiments. The idea is called ocean fertilization. You add small particles of iron to the ocean and to stimulate photosynthetic organisms. It's a disaster. It leads to ocean acidification and all sorts of environmental contamination, and it doesn't work. It doesn't even effectively remove carbon. So we're not going to look at that side of this figure at all. Instead, we're going to look at vegetation and soils, and then later on we'll look at rocks. So what does it mean when we carbon offset using vegetation and soil? So we look at that 272 petagrams of carbon and think, can we put some of it in vegetation and soils? Well, we can group the approaches. Now these are getting more, now remember, these are the approaches that when somebody says, well, offset your carbon, this is what they're going to do. So let's understand what they mean. There's two approaches. One are grouped into called natural climate solutions. And there's three categories. And there's a lovely study done where there's been an estimate of what the potential is for natural climate solutions. This is done with a pricing scale, so we see approximate proportions what it actually costs per ton of carbon dioxide. Note now it's per ton of carbon dioxide, not ton of carbon. The Earth's potential from forests is around about 4.4 petagrams of carbon per year. So what does that mean by using forests as a natural climate solution? What we're talking about is reforestation. That means planting trees where there were trees before. I'm going to talk about afforestation later. That's not the same thing. Reforestation is replanting of trees where there were trees naturally. Preserving forests and avoiding forest fires. Those are the three main categories of using forests naturally to, as a store for carbon. Agricultural and grasslands, what does that mean? It's a much smaller contributant, but what are we talking about? We're talking about changing the way we farm so that when we farm, we keep carbon in the ground and don't release it to the atmosphere. We're talking about planting trees in farmland and in cities where there are presently no trees. And we're also talking about novel technologies such as biochar, which are burrowing in soils. So that's what the natural solutions for agriculture and grasslands concern. And then we're looking at wetlands. Now, wetlands are very, very difficult to make. So what we're talking about is wetland preservation. Making wetlands is becoming to be a geological problem. We're very good at draining them and taking them away, but wetlands are an absolutely fantastic sink for carbon. Some studies show that they're orders of magnitude more effective than trees. So draining a wetland to plant trees is not necessarily a smart idea. There are also another group of ways of using vegetation and soils. These are artificial. The term used by IPCC is carbon dioxide removal. This is when we do things unnaturally. And a good example, which one often misunderstands, is afforestation. This is not the same as reforestation. This is planting trees where trees were not naturally before. And there's a very person-centered study, human-centered study, done by these authors, Baston and colleagues, in 2019, where they do a little calculation and show that the potential for, you guys are in the way of me, I can't see my number anymore. I think it says about 200. The potential, I've got all your pictures in front of my number. It's about 200 petagrams of carbon per year could, in theory, be stored by planting new trees. But we've got to be aware what that actually means. What they've actually calculated is all the potentially forested areas allowing us still to feed ourselves. And they calculate an area the size of the continental US. They're not, however, saying it should be the continental US, which maybe one might think is a good idea. Sorry, I said there'd be no value judgments. But what the problem with the study is there's no consideration for other ecosystems. There's no consideration for there could be something else living there where we plant these trees. So yes, it's a huge sink for carbon, this planting of trees, and it's a sink of carbon that's on the right scale as the amount of carbon we put in the atmosphere. But we're not the only inhabitants of this planet. So one has to really think about, is this morally right? Okay, rocks. Let's look at the next one. So rocks can be divided into two groups, both of which are artificial, carbon dioxide removal. There's no natural way of putting carbon into rocks. It's very easy to get carbon out of rocks. Putting it in is not a natural process. The only natural way of putting carbon in rocks is not taking it out of the rocks in the first place. Two categories, one called BECCS and one called DACCS. BECCS is bioenergy, carbon capture and storage. Now I take the example of Stockholm Exergi, who are attempting to do this in Stockholm. It's a good local example. So what does that actually mean? Well, it means that we take carbon from a biological source and we interrupt the natural carbon cycle that's happening quickly. The planting of trees, we burn some trees, release some CO2, and instead of putting it in the atmosphere, as it would have otherwise gone to, we pump it, we make it into a compressed liquid and store it in sedimentary rocks. There's some potential for that, 700,000 tons of carbon dioxide per year. How many jumbo jets is that? It's 3.5. 3.5 jumbo jets. How many jumbo jets do we have to deal with again? That was 5 million times 7.8. Okay, so it's a small contributant. I hope you see that we're talking really quite small. But you compress the CO2, put it in liquids and store it in sedimentary rocks. There's some issues there because it's a liquid and rocks are porous, so of course it might get to the surface. The capacity of some of these formations is huge, but you've got to be aware that these sedimentary rocks, there's a reason there's holes in them today. And that's because oil has been extracted from them to burn. So it's, I leave that for you to think about. The other type is direct air carbon capture storage. And this has been pioneered. Well, the study that most interests me, where they're pioneering this, is in Iceland. And this is basically a great big hoover that hoovers carbon out of the atmosphere. It filters through a membrane, which is made of either some organic substance or the minerals called zeolites, which are pretty little minerals that absorb CO2. Anyway, you absorb the CO2 in that membrane, then you have to heat the membrane up to get the CO2 off it, and then it's compressed and pumped down into bedrock. There is a beauty of this process, which I like compared to the other process, and that is the carbon dioxide is stored in a solid form. You can actually see it. It's the little white crystals in the crack in this rock. That's actually solid CO2. It's the mineral calcite. It's quite beautiful. The capacity at the moment is not very big. One of those machines does around about 50 tons of CO2 per year. So if you'd like to compare that to your jumbo jet, you can see that we've got a bit of a mass problem there. You need a lot of those hoovers. And then of course you need the energy to run them. And that's fine on Iceland when that energy is geothermal. But if you use an energy source where you burn carbon, then it actually might end up not contributing at all. So you need to think the energy source for this type of carbon removal must be renewable. Okay, so I've looked at the different places. Basically, we've got vegetation and soils, and we've got rocks. Let's just go back to this problem of mass and time. And I've got this figure. It was color-coded. The green side was this geological process, volcanoes and weathering. I just want to put the human impact in the right side. The blue one is the natural fast process. Now, if I color code them, land use change is effectively part of the one cycle. That's the fast one. But this huge fossil fuels and cement production, that's just burning rocks. So if we're burning rocks, it's part of the geological scale. So let's just look at those So we're looking at a tens of years process on one side, that's one time scale, and a millions of year process on the other side. We're also looking at an enormous mass on one side and a slight smaller mass on the other side. So there's a real problem with mass and time here. You can have to ask your question, can you plant trees on the left of this figure and solve the problem on the right of the figure? So on the left of the figure, we're looking at tens of years. To be fair, probably even hundreds of years. And that's what we do when we plant trees. And you can do a lot with planting trees, as some studies have showed. If you don't care about any other ecosystem, you can remove a lot of carbon. The millions of years, we can't do very much of it yet. 50 tons of carbon per year for every Hoover. That's not much of a fraction of a 200,000 ton jumbo jet. And we have 5 million of them per petagram and 7.8 petagrams. You see the problem. I hope. And let's just really get that problem of time enforced. Allow me to make 1,000 molecules of CO2. I'll just fill the atmosphere up with CO2. Well, that was quite quick. And let's see, even though I took 10 years over that. Well, after 100 years, 75% of that CO2 is still in the atmosphere. What's the lifetime of a tree? 50 to 70 years? So I planted a tree. Did I really solve the problem? After 1,000 years, 40% remains. After 10,000 years, 25% remains. So we really have a time scale issue here. And then let's look at the problem of proportions. Now, I'm going to take the IPCC's 1.5 degree pathway to illustrate that. Now, remind you what that pathway shows. It shows a pathway to keep Earth's atmosphere such that global warming does not come above 1.5 degrees. A couple of things to be aware about that pathway. One, it gives you a 66% chance of success. So 2 out of 3 chance. And to keep what that means in mind, if you have a 2 out of 3 chance that the airplane you get on to go on your big carbon burning holiday to Thailand has a 2 out of 3 chance of getting there, would you get on the airplane? So let's just remember what that means. Okay, that's one of the things. The second thing, this doesn't consider tipping points because it's really hard to understand tipping points. So this is it's the pathway to work from, and it's very useful to work on the proportions. So let's look at the proportions in that. What is that carbon reduction made of? It's made of a switchover from land use emitting carbon to the atmosphere to land use consuming carbon, and a reduction in fossil fuels, consumption in industry, and CDR is this artificial bit that we have to somehow artificially remove carbon by technology that we haven't got yet. Okay, that diagram can sometimes be a bit hard to understand, so let's look at it a different way. Let's break it down. We've got sustainable land use, we've got renewable energy and sustainable industry, we've got reduced consumption, and we've got carbon dioxide removal. Those are our tools. That's our toolbox for solving climate. What does the IPCC's proportions tell us? We can rely about 20% on what we do with the land. Planting trees, preserving wetlands, you name it. Conservation agriculture. 70% is this part. Generating energy that's from renewable sources and reducing consumption. And it's only 10% that we're thankful at this point. Our reliance on carbon dioxide removal is at 10%. That assumes that we really pull our fingers out and get carbon emissions down like yesterday. That increases if we don't do anything, that number just gets bigger and bigger and bigger. And that's a problem because we don't know how to do it. So that's not a good thing. But if we think about the proportions problem, well, if you plant trees, you're in the 20% box. The 70% box is about reducing the amount of energy we use and not burning rocks. So we need to have all that in mind when we talk about carbon offsetting. Now, I hope I haven't given any value judgments whatsoever about carbon offsetting in that entire talk. I've just hopefully set a stage for what I hope will be an interesting discussion. Thank you very much.